Today we will be discussing about theory of resonance. Resonance theory says that whenever a molecule can be represented by two or more structures that differ only in the arrangement of electrons, there is resonance. The molecule is a hybrid of all these structures and cannot be represented by any one of them. Each of these structures contributes to hybrid. So that says that a molecule can be a hybrid of two or more structures that differ in the arrangement of electrons. This is the first point of resonance theory. And what is the second point? When these contributing structures are of same stability means same energy, resonance is more important. The contribution of each structure to the hybrid depends upon the relative stability of that structure. The more stable the structure, that particular structure makes more contribution. So what is the second point? According to this resonance theory, the second point says that if the contributing structures have same stability, resonance is more important. And if one of the contributing structures possesses more stability than other contributing structures, its contribution to the stability of the resonance hybrid will be more. And what is the third point? The third point says that the resonance hybrid is more stable than any of the contributing structures. So this increase in stability is called resonance energy. As I mentioned, the more equivalent stability of the contributing structures, the greater is the resonance. So these are the three key points of resonance theory. So we can brief in such a way that resonance theory says that a molecule can be a hybrid of two or more structures which differ only in the arrangement of electrons, and these contributing structures can contribute to the stability of the hybrid, and if the contributing structures are of same stability, the stability of the hybrid will be high and the resonance hybrid will be having more stability than any of the contributing structures. Allyl radical, it is a resonance hybrid of two structures. So as per resonance theory, whenever a molecule can be represented as a hybrid of two or more structures, its stability will be high. So we can apply the same principle to the stability of allyl radical as it is a hybrid of two structures, and we can see that these two structures differ only in the position of the double bond as well as the position of the odd electron. So allyl radical, it has a structure that is intermediate between 1 and 2. So structure here we can see that the structure 1 and 2 are exactly equivalent and they have got the exact same stability. And as we learned in the previous section, if the contributing structures they have exactly same stability, their contribution to the stability of the hybrid will be equal and the stability of the hybrid will also be more. So as per resonance theory, allyl radical does not contain one carbon-carbon single bond and one carbon-carbon double bond. So it contains two identical bonds, each one intermediate between a single and a double bond. And you can see in the structures, in structure 1 there is a double bond between the first two carbon atoms and the odd electron is present on the other side carbon atom. But here in the second structure, the odd electron is present on the first carbon atom and the double bond is present between the middle and the last carbon atom. Actual structure of this allyl radical is a hybrid of these two structures where there is a single bond and a half bond between the first two carbon atoms, again one single bond and a half bond between the middle carbon atom and the last carbon atom. That means there is a 1.5 bond between two carbon atoms, and the odd electron is present over, or it is delocalized over both the terminal carbon atoms. So it is said that the odd electron is not localized on one carbon or the other, but it is delocalized, being equally distributed over both terminal carbons. The stability of allyl radical. We know that the resonance hybrid will be having always more stability than the contributing structures. The allyl radical is more stable and its stability parallels with that of a secondary radical. As far as an unsubstituted allyl radical is concerned, it is like a primary radical, but its stability is somewhat similar to that of a secondary radical. What is the reason behind this stability of the allyl radical? Now we have an idea that allyl radical is a hybrid of two structures. So by applying the resonance theory, we can explain the stability of allyl radical. So as a resonance hybrid, the allyl radical is more stable. That means it contains less energy than either of the contributing structures. The additional stability possessed by the molecule is referred to as resonance energy. The extra or the additional stability possessed by a particular molecule due to resonance is known as resonance energy. Since the contributing structures are of exactly same stability, stabilization due to resonance is large. We have mentioned in the previous slides that the structures of the contributing structures of allyl radical is it is having same structure, same stability, and their contribution to the stability of the hybrid will also be high. The resonance stability of allyl radical is estimated by comparing two reactions. That means normal propyl radical, it is formed by the homolytic bond dissociation of propane. Propane undergo homolytic bond dissociation energy to form normal propyl radical, that is a primary radical, and the bond dissociation energy is 98 kilocalories. Okay, and for this allyl radical, it is obtained from propylene by homolytic bond cleavage, and the allyl radical is formed with a bond dissociation energy of 88 kilocalories. That means there is a reduction in the bond dissociation energy. So this reduction in bond dissociation energy explains why this allyl radical is more stable. That means if the energy content is more, that much and less energy is associated with this allyl radical, that means that much stability, that much more stability is incurred with the allyl radical. Propane, the normal propyl radical, propylene are each represented by a single structure. Allyl radical is a resonance hybrid. The energy difference between propylene and allyl radical is 10 kilocalories per mole, less than the energy difference between propane and normal propyl radical, that is 98 minus 88. The lower bond dissociation energy is due to resonance stabilization of allyl radical. So the resonance energy of allyl radical is 10 kilocalories per mole. We can say the extra energy is represented as resonance energy. For allyl radical, the resonance energy is 10 kilocalories per mole. So what contributes to the high stability of allyl radical? So it is attributed to its particular orbital picture. So we know that in allyl radical, each carbon atom is bonded to 3 other atoms, and whenever the carbon atom has to bond with the 3 other atoms, it uses sp2 hybridized orbitals. So while forming sp2 hybridized orbitals, the individual orbitals involved are 2s, 2px and 2py. So these 3 orbitals undergo hybridization, that is intermixing of the orbitals, and we will get, and the carbon atom will possess 3 new sp2 hybridized orbitals that are equivalent in all aspects. So the 2p Z orbital is not involved in hybridization. So each carbon possesses a 2p orbital with an odd electron that is not involved in hybridization. Overlap of these 2p orbitals with the 2p orbitals of carbon atoms on either side leads to the delocalization of electrons. We know that the sigma bonds are formed by overlap of sp2 hybridized orbital. So in the first carbon atom, the carbon atom is bonded to 2 hydrogen atoms and 1 carbon atom. So it uses sp2 hybridized orbitals. The sigma bonds are formed by overlap of axial overlap or face-to-face overlap of hybridized orbital. But for each carbon atom, there is a two-piece orbital that is not involved in hybridization, and moreover it possesses an odd electron. So this two-piece orbital can overlap with the carbon atoms on either side. So as a result, as shown in the orbital picture of the resonance hybrid, the central two-piece orbital of the central carbon atom can overlap with the two-piece orbitals of carbon atoms on both the sides. That results in the delocalization of electrons. That is the structure or the orbital picture that corresponds to resonance hybrid. So the explanation for the orbital picture of structure 1 and 2 and the orbital picture of hybrid is given or discussed in this slide. So regarding the orbital picture of 1 and 2, p orbital of one carbon atom can overlap with the p orbital of adjacent carbon atom, permitting the electrons to pair and a bond is formed, that is the double bond is formed. This gives rise to contributing structures 1 and 2 with odd electron occupying the p orbital of the remaining carbon atom. So the double bond is formed by overlap of two-piece orbital of first carbon atom with the two-piece orbital of the central or the middle carbon atom. If there is a double bond between two carbon atoms, that is formed by overlap of or the sideways overlap of two-piece orbitals, and the carbon atom on the other side that possesses a two-piece orbital with an odd electron. This is the orbital picture that corresponds to structure 1 or 2, vice versa. Regarding the orbital picture of hybrid, p orbital of the middle carbon atom can overlap equally well with the p orbitals of both the carbon atoms to which it is bonded. That means the capability of the two-piece orbitals to overlap equally well with the two-piece orbitals of carbon atoms on both the sides. So the result is a two continuous pi electron cloud, one lying above and one lying below the plane of the atom, because the two-piece p orbital it has two lobes. The overlap of p orbitals in both the directions and the resulting participation of each electrons in two bonds is equivalent to description of allyl radical as a resonance hybrid of two structures.